Today what we're going to focus on are the other two cases of solutions to systems of differential equations. The first one being repeated eigenvectors. What happens when we get repeated eigenvectors? So remember on Wednesday, last time I saw you, we talked about real distinct eigenvectors. Today we're going to look at repeated and then complex, assuming we have time for both. So we're going to start with repeated, and the process really is the same. There are some weird nuances that go with repeated. Remember when we did repeated roots for second order linear differential equations? We would just add a t in front of the next term. It's kind of going to be the same similar idea, but there is an additional vector. Because when we go to find our eigenvalues, we need as many eigenvectors as there are eigenvalues, and there are two eigenvalues. The problem is they're the same. So if we use the same vector, they wouldn't be linearly independent. So we have to go through another step with these eigenvectors. So the first thing we would want to do in solving, this happens to be an IVP, so we'll take that step at the end. But the first thing we'd want to do is to actually find the eigenvalues. Okay? So walking through the process to find the eigenvalues, I'm going to show you a couple shortcuts that I will start taking, and probably you should too, just to simplify the process a little bit, if it makes sense to you. So remember, the process to find the eigenvalue is we take and do A minus the identity times lambda, right? And then we set that equal to 0 after we find the determinant of this. Remember, that's the process we go through. And before, what we had done is we had gone through and showed all of the steps. And these are the steps I'm hoping we can start to skip a little bit. We would go through and say, okay, this is 7, 1, negative 4, 3. And I'm going to subtract lambda times 1, 0, 0, 1. And it's going to equal 0, 0. Right? And then we'd go through and do that subtraction, the multiplication by lambda. I'm hoping we can get past that and go straight to the idea of the determinant. So really what I want to find is the determinant of 7 minus lambda, 1, negative 4, 3 minus lambda. So I'm hoping we can forgo this process and move straight into the determinant. And the determinant, where's the 2? 7 minus lambda, 3 minus lambda, minus negative 4. And that determinant needs to equal 0. So that's my goal. Skip the intermediate step and go straight here. And I'm going to show you one other shortcut as well here in just a second. If you find value in it, use it. If not, that's okay. If we FOIL these, we'd get 21 minus 7 lambda minus 3 lambda, so minus 10 lambda. Lambda squared. What did we say? 21 plus 4? And so factoring this, we'd get lambda minus 5 squared equals 0, which means lambda equals 5, and it's repeated. Multiplicity of 2. Yes, good. Okay.
Is there a reason that doing the normal steps won't work for repeated roots?
From now on, you will see, like when you see the homework answers, which I didn't post yet, actually. When you see the homework answers, there's going to be quite a few steps skipped. Like, I'm not going to give you that step listed in gray. I'm going to go straight here. Because all of them start the exact same way. And I know that's what the end result's going to be. I'm also going to show you another step here that I'm going to start skipping, and I'll explain why. We know in order to find, now the goal is to find, we know the eigenvalues. It's 5 and 5. So now my goal is to find the eigenvectors associated with 5. But to find those eigenvectors, remember we take this A minus the actual lambda I and set it equal to 0. And so for our problem, it would look like 7 minus 5, which is 2, 1, 0. And then negative 4, 3 minus 5, which is negative 2, and 0. And this is the part where we're going to start taking some shortcuts if you feel comfortable. If you can see the pattern. But if you can't, that's okay. Take all the time you need. We know that at this point, what we have done in the past is we have done the REF function on our calculator, which gives us this expression. In this problem, it looks like this. Okay? And I'm hoping you trust me on that. Give you something similar to that. But I'm going to back you up in just a second, because this step right here is the step that I would actually skip. I would skip this step. And let me show you what I mean. Notice that each of the equations, or the equations, I guess we could say, or the rows in the matrix, 2, 1, and 0, negative 4, negative 2, 0, are just scalar multiples of each other. Do you see that? That happens every time. And so because they're just scalar multiples of each other, really all we need to do is to consider one of those equations. We don't really need both of them. We just need one of them. So you are welcome to pick either one, whichever one makes the most sense to you, or the one that looks simpler to solve, I guess. So for example, since they're just linear multiples of each other, I might just pick this equation, 2x1 plus x2 equals 0, and work to solve this. It's the same thing we'd get with the REF. It's the same exact function we would get. And when we do this and solve this, what do I get here? We would get 2x1 equals negative x2. And then the vector I might be working with here, we're going to call it vector v. I guess I could do brackets. I've done brackets on all the other ones. Vector v could be, actually it doesn't really matter which one it would be, but vector v in this case, if we let x be 1, x1 be 1, then x2 would be negative 2. Yeah? Okay. The problem is we need a second linearly independent vector. But if I go through this exact same process with the second eigenvalue, which is also 5, will I come up with anything different? No. So here's where the process needs to be a little bit different. For repeat vectors, for repeat eigenvalues, what we want to do is we want to find a vector, we'll call it W, such that A minus lambda I times W, that vector we don't know, equals that first vector we just found. So this vector here, this vector v, is the first vector we found. So our goal is to now find an additional vector such that the original problem times this new vector equals what we had. Let me show you what that looks like in equation form and then talk about how we would solve this. We know our A minus lambda I would be 7 minus lambda, which was 5, so it would be 2, 1, negative 4, and then 3 minus 5, which is negative 2. And so my goal now is to find some vector W such that it equals the vector we just had. Now I could write this as an augmented matrix, 2, 1, 1, negative 4, negative 2, negative 2. But you'll notice again that these are linear multiples of each other, right? If I could multiply vector 1 by negative 2, I would end up with vector 2. So you could go through the REF process, or we could cheat the system just a little bit and say that 2 times W1 plus 1 times W2 needs to equal 1. Which if we solve for one of these vectors, we would get W2 equals 1 minus 2W1. And now what we're going to do is we're going to pick a new value for this vector. So I'm not going to use the same values I used before. It shouldn't work anyway, even if I did. So let's let W1 be 0. That would be the easiest. What would W2 be then? 1. And so my new vector, my second linearly independent vector would be 0, 1. Okay, so here's the notation for how we express our general solution for repeated eigenvalue, for the repeated eigenvalues, is we're going to go back here. So it says x, the solution is C1 e to the lambda t v, that was our first vector, plus C2 times. You'll notice we're going to take that C2 and multiply it by t. It's very similar to what we did with repeated values from before. E to the lambda t times that vector. So notice the vector that we use, that repeated one, just has a t in front of it. But we're going to also add to it e to the lambda t times that additional vector that we found, that unknown w vector. So my general solution would look something like this. We would say that x, this vector, equals C1 e to the lambda t, so 5t, times that first vector, which was 1, negative 2, plus C2 times t e to the 5t, again times that first vector that we found, plus e to the 5t times that second vector we found. And this would be my general solution. I didn't leave myself much room on this. However, we still need to use our initial condition. Oh, see, that's why there's a whole page.
That's why there's a whole page. What if I already used the whole page?
So,
Yeah, what if we no longer have a whole page?
well, let's write small.
Oh, yeah. That would have helped a while ago.
To tell you to write small? Chandon, would you write small even if I told you to write small?
I tried to write small.
Do you?
So the answer is no, please.
All right, but here's the beauty of this initial condition. The t value 0. So it will make our life a little bit easier. So we are, oops, that's not negative 2, it's positive 2. 2, negative 5 is what we're aiming for when we plug in 0. You could skip this step. Let me just show you what we're doing.
Where's Jake in the notes? You're linking up those on.
Jake's sick. I don't know where Mo is. I thought he was sick yesterday, but he's still went out, so I don't think he's that sick.
So he's not.
Maybe he ended up being sicker than he thought.
It's every page too.
All right. Here's the beauty of this one. Write just this step if you're out of space. Okay. With plugging in 0 for t, we get this pretty nice system of equations here. Right? We get this system where we have 2 equals C1. That's doable. And negative 5 equals negative 2C1 plus C2. Which means C2 equals 1. And then we could combine our equations, or plug those into our equation. So my x is going to be, we got C1 to be 2. So 2e to the 5t. Did I lose a negative?
I think so, because it's negative 4.
But then I add that negative 4 to the 5, it'd be negative 1. Yep, it is. Good job. Thank you. Yep, you are correct. Thank you. Plus, minus, definitely minus. This is my negative. So that would be negative. I guess I could have written plus a negative. Negative 1 times te to the 5t times 1 negative 2 plus e to the 5t. Sometimes I can't remember what I'm writing. There we go.
Class survey. Does anyone else try to write the division sign when they do the matrix?
Division sign.
Well, like 1 over.
Oh, all the time.
Yeah,
Yes, all the time. In the matrix, right? Is it a fraction?
I definitely do that.
Yeah.
I do that.
It's worse if I'm like, there's a 5 in there. There are other ways this could be simplified. We could combine this by distributing that negative in through the problem. And then what you would see, we could expand it all out and condense it. I can show you that at another time. You don't want to do that now? No. Okay. You've had enough. You'd rather see it?
Sleep.
Oh. You guess what you get to do tomorrow?
Sleep in.
Oh my
For the first
gosh.
time in like a month.
Sleep in.
Except for last Friday. Oh, you didn't have class.
But Jack was still here. Okay, so now we're going to look at complex eigenvalues and what happens with that. As a reminder, Euler's formula says that e to the a plus ibt equals e to the at times cosine bt plus I sine bt. We've done this before. Remember we did this with the complex. Don't remember that. It's all right. We'll come back to it. There's no numbers yet. No. Okay. So when we have complex eigenvalues, I'm really only going to use one of the complex eigenvalues to get the solutions, because in order to get two solutions, I'm going to go back up here just for a second. In order to get two solutions, the two solutions I'm going to end up with are going to be the real part is usually notated with RE times some vector x of t, and my second solution is going to be the imaginary part times that same vector x of t. This is my goal. So I'm going to have a real part and an imaginary part. Where that's coming from is from the idea of Euler's formula. And again, we're only going to use one of the eigenvalues that we get. So let's go through and find our eigenvalues. Again, I'm going to take some shortcuts. I know I'm going for the determinant of 3 minus lambda, minus 13, 5, and 1 minus lambda. So I need to find this determinant, which would be 3 minus lambda times 1 minus lambda plus 60 equals 0. So that is the characteristic polynomial that I'm solving. Say it again.
65.
I can do good math most of the time. Thank you. 65. It was close. We're close.
Would have been 5.
We were not close. Sorry. Is it? Everybody gets a ribbon? That's how we're going to operate this? I like everybody gets a ribbon. Everybody gets a... You guys deserve a goal.
Participation trophies. Do we all get participation trophies at the end of the year?
All right. So if we FOIL this together, what do we end up with? 3 minus 4. So lambda squared minus 4 lambda plus 3 plus 65, so plus 68 equals 0.
I don't know how to do that.
Okay, I will probably complete the square. If we complete the square, we'd be adding 4, right? Subtracting 68, but adding 4 to the other side, so minus 64. Yeah? Completing the square. So, if we complete the square on this and solve, we get lambda equals positive 2 plus or minus 8i. Yes? Are we going blind faith? Can you blind faith this for me? Dress. Yeah, that is true. I did do 13 times 5 equals 60, so. All right.
Yeah, but I don't like imaginary numbers, so I'll delete it.
Okay. It is not. Shoot.
I mean, were real numbers not enough for us that we just decided we're gonna make up numbers?
Yes. Okay. So, I am only going to use one of these eigenvalues to make an eigenvector. Only one. So I will probably choose the positive one more times than not. And so what I need to do is my vector now will be 3 minus, I'm going to write it just so you can see it, 2 plus 8i.
Do we not have two separate, like, different eigenvalues?
We do, but I'll show you how we don't need it. I'll show you why.
Negative 13.
Oops. Yes. Yes. Okay. This is Monday. Good? All right. So 3 minus 2 is 1, minus 8i, negative 13, 5, negative 1 minus 8i. This is the matrix that I'm trying to solve, the augmented matrix. Now, typically we would go through the process of echelon form, row echelon form, trying to get this down. But here's what I'm going to tell you. To cheat the system just a little bit, we know these are linear multiples of one another. They will be. And therefore, if I go through the process of row echelon form, reducing down to row echelon form, I'm going to be able to use just one row.
How do we know that it's a linear multiple?
I just showed you on the last examples. Yeah? This one's not as pretty. It doesn't seem to follow the patterns as well, but it will be. All right, so here's what I'm going to do. I'm going to take and do 5. I'm going to choose it doesn't really matter, but I'm going to choose the bottom one. 5x sub 1 plus negative 1 minus 8i x sub 2 equals 0. And if I move everything over, we would get 5x1 equals positive 1 plus 8i x2. Just changing the signs. It'd be minus all the negatives. May as well just change it. Okay, so at this point, I have several options. If it makes your life happier, maybe we multiply like this to see it better. But what I'm going to do is I'm going to let x2 be 5. I'm choosing 5 so I don't have a fraction in my x1. So if I let x2 be 5, then my vector that goes here would be 5. But my numerator, or not numerator, see, there we go. Not division, not a fraction. The first entry in my vector, if I let x2 be 5, will be this 1 plus 8i. Which looks like a weird not 8i. Let's do that again. 1 plus 8i. Can we do it? Okay. So here's what this looks like. For this first solution, I have e raised to the lambda. Where'd 2 come from? Because A is some of you want to be here tomorrow real bad, huh? Yeah?
Imagine
Your problem, not ours.
Leave them at lunch or something for like an extra hour.
Okay.
Go get pizza or something. Go to Denver.
So, e to the lambda, oops, I lost the t. E to the lambda t times that vector 1 plus 8i and 5. And what we need to do here, we need to eliminate the complex part. Because my solution can't have a complex part in there. So I'm going to start by dealing with Euler's formula for this expression right here. So I'm going to deal with Euler's there. So here's what that will look like.
Why are we only looking at x1 and t and not the entire thing?
We will get to the entire thing because this is going to create both in one. All right. Using Euler's, this will be e to the 2t. Thank you.
And there's one for your daughter too, little socks.
Oh, she will love that. Oh, she'll like that even more. So it'd be cosine 8t plus I sine 8t. All I did was replace this e to the lambda t with getting rid of most of the complex part. We'll get to more. We'll eliminate more. That will be times this vector, 1 plus 8i 5. Okay. And now what we're going to do is going to be a bit messy. What we're going to do is we're going to ignore the e to the 2t part. So we're going to ignore this part right here, and we're going to multiply this cosine 8t plus I sine 8t by 1 plus 8i, and by 5. So I'm multiplying these two together. You'll see in just a second. Okay. Are we writing small? Not small enough?
It's gotten smaller, but like, it's still more.
Good. Okay. Here's what that's going to create. I'm really multiplying a scalar by a vector. So what I'm going to have is still a vector. A 1 by, sorry, rows by columns, 2 by 1 vector is still what I'm going to have. And it will get nice, but it doesn't start nice. Are you ready? When I multiply, you mean yes, you can't wait.
Okay.
I knew it.
Sure.
Oops. Sorry. When I multiply cosine 8t in here, I'm going to get cosine 8t, because that will be times 1. And then I'm going to multiply cosine 8t by 8i. So I'm going to get plus 8I cosine 8t. I don't know why I put parentheses on that AT and not the others. Plus, now I'm going to repeat that with the sign. So we would get plus I sine 8t times 1 plus I squared, or plus 8I squared sine 8t. What happens there?
Wouldn't it be I cosine 8t because it's a cosine in the
I multiplied cosine 8t by 1, cosine 8t by 8i. I sine 8t by 1, I sine 8t by 8i.
I did it the other way.
That's fine. Now, why is that advantageous? Well, that will simplify. Now I'm going to do that times 5. 5 makes it easier. So we get 5 cosine 8t plus 5I sine 8t. Okay.
Isn't that just a negative 1? Because it has-
Yes, that was my next question. So we know that this expression right here, 8I squared, is really the same thing as saying negative 8. Do we agree with that? Do you remember I squared is negative 1? Yeah. And now what I'm going to do is I'm going to pull apart my real and my imaginary. So what that looks like is I have e to the 2t, and my real parts up here, I have cosine 8t and negative sine 8t. So I get cosine 8t and negative 8 sine 8t. And my real part in the second row is the 5 cosine 8t. I don't know why it's in blue at the moment. 5 cosine 8t. Then my imaginary part is going to be, I'm going to factor the I out. So it would be e to the 2t. And then we'd get 8 cosine 8t plus sine 8t and 5 sine 8t. So notice we just factored out the imaginary parts. So my imaginary parts with the I came out of each of these expressions and moved to the front. These actually form our general solution. Remember in the beginning, we said our general solution needed to have, I'll go back, a real part here times some vector and an imaginary part times some vector. And that's my two solutions. So my general solution is C1 e to the 2t times that vector of cosine 8t minus 8 sine 8t, 5 cosine 8t, plus, here's the beauty of that, we know it needs to be the imaginary part, so we're just going to call this C2 e to the 2t, where C2 could be part of that. 5. Oh, this is 7 initial value. Yeah, that wasn't kind.
Yeah. We could, this is the hard part. That's alright. We can skip it. Yeah.
Okay. You get the idea?
Yeah, I don't know.
Okay. So since we're able to find two linearly independent solutions with a single eigenvalue, we don't have to use the second eigenvalue. My whole goal is to find those two, and we did. We found one part of the real, one part of the imaginary, and then we would go and plug it back in, the initial value. It actually works out decently well on this one. It's not great. I mean,
What's done?
That's done is done. So that is how we deal with the imaginary eigenvalues. Questions?